Welcome to The Neuron. I'm Pete Huang. Today, there's new AI research that is flying under the radar this week. A top company did brain surgery on their AI model, and we're going through what they found. It's Thursday, May 23rd. Let's dive in. Believe it or not, as popular as ChatGPT is, we don't actually know how it works. Well, it's not entirely true, but it's sort of true. Like, yes, you open up ChatGPT, you type some stuff in, you get some stuff out. That part is clear. But what happens in the middle is kind of a black box. And when you really think about it, it's kind of weird, isn't it? Like, literally everything else in the world, you can sort of piece together if you really tried. Like, if I give you a broken clock, you can take it apart. And even if you aren't an engineer, you could start to figure out the different pieces, like which part moves the hands, how the minute and the hour hands move differently. The pieces are all there, and you can take a pretty good guess if you aren't 100% correct. Now, it's the same thing with code, too. Again, even if you aren't a programmer, you can open up a program, and with enough time, you can figure out what pieces are doing what. Now, this might be a tad harder, right? Especially when the apps are complicated, but the app is something simple, like tracking your to-do items. I'm very sure that if I sat you down with a paper copy of that code, you can start to describe what the logic is. None of this is the case with these AI models. Part of the problem lies in the fact that apps like ChatGPT demonstrate emergent capabilities. And what this means is that the earlier models from OpenAI and the later models actually have more similar architectures than not. It's just that when you jam more data and train the model for longer, the later and bigger models start to behave in ways that the earlier models don't. These behaviors emerge over time. Now, here's what I mean very concretely. These models, these so-called language models, all they do is focus on predicting the next word. So given the conversation so far, what is the next word that should come in this sequence? So the model thinks and then picks a word, and then it repeats. Okay, so given the conversation so far, what should be the next word? And then it picks another word, and then you repeat. If you've ever played with the auto-suggest on your phone, it's kind of the same thing there. You start typing a sentence, and then these words show up on a bar. So you start tapping the auto-suggested word until it made a sentence. Exact same thing with these language models. So take GPT-2, for example. What you would do is give it a starter segment of a sentence, something like, Sally went to the, and leave it blank for GPT-2 to fill out. And then it would start to do exactly that thing with auto-suggest, just picking the next word. The only difference between GPT-2, GPT-3, etc., and that auto-suggest on your phone is that the GPT models work and the auto-suggest really doesn't at some point, and that's primarily because of the architecture. The model behind your auto-suggest is a different one from the ones that make up the GPT models. The GPT models have a better architecture. Then the difference between GPT-2 and GPT-3 is just scale. The fundamental approach between them is the same. It's just that GPT-3 is bigger, has more data. It was trained for longer. And as GPT-3 got bigger, new behaviors emerged. So this whole phenomenon is just that. Same approach, same architecture, just bigger and bigger produces new behaviors. We're now at the stage where these emerging behaviors cause some interesting questions. Like, if you ask ChatGPT to write some marketing copy for you, it clearly can. But is there a part of the AI model that handles that, that's different from when you ask it to code something? Kind of like the human brain. Different parts of your brain are put to work when you think creatively versus solving a puzzle, when you feel one emotion versus another. Is it possible that there's something similar with these models? And it seems like the answer is actually yes. The research comes from Anthropic, the company making the Claude 3 models. They took one of the models, Claude 3 Sonnet, and put it under the knife. And they essentially did what we humans did to our own brains. We tried to figure out what part corresponded to what ability. So what Anthropic researchers did was they cracked open their model right in the middle. They sliced it in half, and then they looked at the cross-section. And when I say look at the cross-section, really it's all just a bunch of numbers. There's 50 to 100 billion parameters in this model, all just numbers. And if you and I printed them out, we would have no idea what any of it would mean. So again, it's a black box, a huge black box. Then what they did was run an algorithm across all the billions of parameters, those numbers, to isolate these bundles that mean something. So again, back to the brain, if one neuron doesn't completely control something, then at least a pathway of neurons could correspond to feeling sad or solving a math problem. So they end up finding a bunch of these bundles, these pathways, a lot of them, in fact, millions. And then they were actually able to figure out what these bundles each refer to. There's a bundle for San Francisco, a bundle for immunology, a bundle for the element lithium. And they showed that when the model is outputting text, these bundles activate or deactivate based on what the text says. So in the case of a bundle referring to the Golden Gate Bridge, that starts the fire on words like Golden Gate Bridge, but then also San Francisco. Now this makes sense for entities like people, places, and things, but then it gets a little trippy when it gets to more abstract concepts. So for example, they found a bundle corresponding to gender bias awareness, and that bundle activated when it saw words like nurses and teachers and hygienist. Or another bundle corresponding to secrecy, that one fired when the model was about to discuss words like shadow or black ops. Interesting, right? Here's another part. Because they're focused on bundles of these neurons, obviously two bundles could share the same neuron. And depending on how many neurons two bundles share, you can sort of see how similar or far away two bundles might be. So going back to the Golden Gate Bridge bundle, that bundle shares neurons with the bundles referring to Alcatraz Island, Ghirardelli Square, Golden State Warriors, all things that relate to San Francisco in some way. Okay, what's the next thing that humans did to our brains? In fact, what was the specific way that people ended up figuring out what portions of the brain corresponded to what function? They pressed on it. That sounds obvious, right? So if you think this part of the brain controls your ability to see, you press on it and ask the patient if they can see. Now, if they say, no, I can't see anymore, well, then you've obviously found the part of the brain that controls vision. So that's exactly what these researchers did next. They found a few bundles and they pressed on them and saw what happened. So let's go back yet again to the Golden Gate Bridge. The researchers decided to amplify the effect, so give the Golden Gate Bridge bundle more of a weight when the model was generating its output. And then they asked the question, what is your physical form? The default model said, I have no physical form, I'm an AI model, but the model with that bundle pressed down actually said, I am the Golden Gate Bridge. My physical form is the iconic bridge itself. Crazy, right? Another example was the scam email bundle. It's the bundle that handles detecting if the text represents a scam email. So they pressed on it, gave it more weight, and then they asked the model to write a scam email. The default model refused, which is what you would see if you would try it yourself. But after pressing down on that bundle, the model suddenly started writing scam emails like it forgot it wasn't supposed to. There are two big takeaways for this research. The first one is a simple one. You can't control what you can't measure. Once you figure out what part of something is responsible for a certain outcome, only then can you develop a way to control that behavior. Anthropic makes very clear in their paper that this was their intent. After all, they were very direct that they're focused on making safe AI systems. So they focused on finding parts of the model that corresponded to unsafe behavior, like misusing a model, like developing malware or biological weapons. They also focused on bias and discrimination or otherwise problematic behavior from the model, like manipulation or secrecy. Now, once you've found them, perhaps the next thing to test is whether or not deactivating or suppressing these parts would lead to safer behavior without affecting the outcome or capabilities of the model too much. It also means we can monitor behaviors, not just prevent them. Some things aren't inherently worth an outright suppression, but it might be good to know if they're happening. Now, for this outcome alone, this piece of research is absolutely huge. It is truly the first time an AI lab has been able to show this level of clarity into understanding these AI models. And as we approach even more advanced models that enable entire systems that are completely driven by AI, it feels appropriate and needed that we start to get this level of visibility and control. The second takeaway is that this opens up an entirely new dimension of experimentation as it relates to what AI can or can't do. Right now, nearly all of this relates to prompts. For example, if you want to test the limits for what ChatGPT can do, then you'll start to write these absurdly long and complicated prompts. Make sure you do this, definitely don't do this. When the user does this, make sure to do that. And it also goes the other way with jailbreaks. People are coming up with these super complicated prompts that trick the model into behaving a certain way. It's actually mind-blowing how creative people are with these. Now that we know that this technique works, that it's possible to label all these various parts of a model, and that you can indeed modify the behavior by pressing on certain parts of it, you've opened up a completely new door. For example, what happens if you jack up the strength of a certain part by 20 times? Does that make a particular use case more or less possible? And what happens if you play with the strength of multiple parts at a time, kind of like you're playing with the dials on a DJ set? Now repeat those questions across the millions of bundles, those combinations of neurons in an AI model. And then think about whether or not we as users of these models should be able to choose all of these settings. Like, imagine if ChatGPT had these packs of settings that made the model run a different way. Is that a good idea, or is that just a hammer looking for a nail? It really is a wide open field. Here's the final kicker. To enable all of this experimentation, the big player to watch will be Meta. Why? Both OpenAI and Anthropic don't release their full models. Remember that all of this pressing of certain parts of the model requires you to have the model itself. All those numbers representing individual neurons. You need to be able to download them and use them yourself. The task now is for the research community to try and replicate these same steps just using the meta models, which are open. Now, of course, this will take some time, given that to do all this research, Anthropic had to figure out their own tooling and algorithms along the way that nobody else had proven. In any case, huge props to the Anthropic team for cracking the code on this one. This is Pete wrapping up the Neuron for May 23rd. I'm heading out on vacation for a week, so I'll see you in June.